we propose Seer, a compliant End-Effector and root control abstraction for humanoid Loco-Manipulation, together with a 3-layer hierarchical framework. Seer has 2 defining features. First, it is compliant, which makes contact-rich interaction safer and more stable. Second, it is controlled only by End-Effector targets and root commands, instead of full-body joint targets. This gives us a much more interpretable and planner-friendly interface for whole-body control. Now let's think about the future form of a general-purpose robot. One possible direction is a single end-to-end model that takes an all-high-dimensional perception and directly outputs fine-grained actions at high frequency. But with current computing and data limitations, that is still extremely challenging. A more practical alternative is a hierarchical system, where high-level planning and low-level control are separated. In a typical hierarchical system, the high-level planner takes perception and task commands as input and outputs command for the low-level controller. However, most existing humanoid motion tracking controllers require a full-body joint target as input. This raises a key question. Can a high-level planner realistically generate such detailed joint-level commands? Generating dynamically feasible full-body joint trajectories is extremely difficult for a high-level planner. This makes current low-level motion tracking policies hard to integrate with advanced high-level modules such as diffusion policies, vision language action models, or vision language models. So what we need is a unified command interface between high-level planning and low-level control. In our design, we choose End-Effector targets as the main representation for manipulation and root motion commands for locomotion. To train a policy that takes End-Effector and root commands as input, we introduce a target joint estimator. This module takes the End-Effector and root command together with common robot observations and predicts a 29 DOF joint target. In addition, to improve safety and performance in contact-rich tasks, we model motion tracking with a simple spring-like compliance formulation. This compliant behavior is then incorporated into training through reward design. With the target joint estimator, we can naturally integrate our method into a standard teacher-student training pipeline. We replace the original whole-body joint command with the End-Effector and root command, connect the estimator output to the student policy, and train them together. In this way, the student learns to produce coherent whole-body behavior from a compact and interpretable End-Effector and root interface, using a curated mass motion dataset for pre-training. Once trained, the student policy serves as a general low-level foundation controller. Built on top of it, we develop different mid-level modules, including teleoperation, locomotion, and manipulation skills. At the top level, we use a large language model-based task manager as the high-level planner. For teleoperation, we provide both VR and keyboard interfaces. For locomotion, we use an A-star planner to generate a trajectory and a tracker to convert it into root commands. For manipulation, we include skills such as grasping, releasing, and alignment. These skills can be programmed, learned, or powered by foundation models. Although these modules are very different in form, they all output the same unified End-Effector and root command, which can be directly consumed by the low-level Seer policy. For example, if the user gives the natural language command, grasp the box, the task manager first queries the environment, reasons about the task, selects the grasp skill, generates the corresponding End-Effector and root command, and sends it to Seer. The robot then executes the grasp through the low-level policy. Now that we have introduced the full architecture, let's look at how it performs in practice. We first show teleoperated contact-rich tasks to evaluate Seer itself, and then long horizon room scene tasks to evaluate the full hierarchical system.